Hello and welcome back on the second video of the series on multivariate calculus. Now we're going to analyze and compute surface integrals or double integrals. First, we are going to define the regions of integration. So we want to integrate a function over a region that is a subset of R2. We restrict ourselves to scalar fields for functions because integrating a vector field would just imply applying a similar procedure to various components. So we can consider three types of regions. Type 1 region is a region that is bounded by functions that are dependent on x. So in this picture we see that we have a constant bounds for y, while for the bounds in the x direction, let's say, we have a function gamma that depends on x and a function delta that depends also on x. Then we have the second type of regions, that is a region D that is bounded by functions that are dependent on y. Here we see that is the opposite, but the bounds are dependent on y instead than on x. The third region, the region type 3, is a combination of a region type 1 and type 2. We can now define surface integration. We have that if f is continuous on a type 1 region D, described by D being all the points in the xy plane such that x is in between a and b, two constants, and y is in between gamma and delta, two functions, then the double integral of f is equal to the integral from a to b, then the integral from gamma to delta of f, and we have to be careful that the dy and dx has to appear in this order, because dy refers to gamma and delta, since y goes from gamma to delta, while dx has to appear after, since x goes from a to b. We have some examples here of type 1 regions. So to recall the regions that are bounded by functions that are dependent on x. As an example here, we want to find the mass of a triangular lamina with vertices on the origin, on the point 1, 0 and the point 0, 2. The density function of the lamina is given by the function 1 plus 3x plus y. We have a drawing here. In this drawing, we can note that the region is of type 1, since the bounds depend only on x, and then we can proceed to find the mass. We know that the mass of the lamina is given by this formula, so we just integrate the density of the lamina over the region. Proceeding like with the formula we just saw, we find that this is equal to the integral from 0 to 1, because here x can go from 0 to 1, since this is corresponding to the dx. Then the integral from 0 to 2 minus 2x, which is the bound that we saw for y. And then we integrate, we have as integrand the function, the density. This is then equal to the integral from 0 to 1, and then we evaluate the inner integral that we found for dy. So 1 becomes y, then we have a 3x gives a 3x y, and the y gives y squared over 2. The bounds for this are 0 and 2 minus 2x. So then solving even further, we get, of course, if we substitute the bounds inside for y, we get this function multiplied by 4, and substituting integrating further, we get here x and here minus x cubed over 3 with bounds 0 and 1. That substituting further will give us 8/3. Now we can move on to region D being of type 2. In this case, the procedure is similar. So if f is continuous instead of in a type 2 region, this region being defined as the point on the xy plane such that y is in between two constants and x is in between two functions depending on y, then the double integral is equal to the integral from c to d and then the integral from alpha to beta of the function. Here we have to be careful that the dx and dy are swapped. This is because now dx refers to beta and alpha as bounds, and the y instead refers to c and d. Some examples of type 2 regions are these, where the similarity in all of them is that they are bounded only by functions that depend on y. Then we can see an example of an integration in a type 2 region. In this case, actually, we want to evaluate the iterated integral, this one from 0 to 1 and then from x to 1 of sine of y squared dy dx. Here we see instead that this would be a type 1 region, but we note that it's not possible to integrate sine of y squared dy because this will not be an elementary function. To get a result from this integral anyways, we can change the order of integration. We first visualize the domain D over which we are integrating, and we see that we can easily write it as a type 2 region, as this bound can be dependent on y, and in every other bound we just have constants. So we see that the double integral in the region D is equal to the integral where x goes from 0 to y, so as we see here in the arrow, and y goes from 0 to 1. In this way, we covered the whole region that we wanted to integrate, and we can just proceed to calculate our double integral. So we get the integral from 0 to 1, and then we integrate sine of yx towards x, but in this case nothing depends on x, so we get just x sine y squared. The bounds are 0 and y. Then we just substitute the bounds, and we get this integral. We just now integrate towards y, which give us minus a half cosine of y squared, and our bounds are 0 and 1 as we had before. And so the result for us will be a half 1 minus cosine of 1, because we evaluated y squared at 1 and then at 0, and it will give us this result. In general, we have that any closed region D can be interpreted as a combination of a type 1 and type 2 surface. We can then find any double integral by imposing the appropriate boundary conditions. For example, if we have a region of type 3, we can use this property to split it into a combination of type 1 and 2. So if D is a region that is the union of D of type 1 and of D of type 2 that don't overlap except in the boundaries, in this way, for example, then the double integral on D of the function is equal to the double integral on D1 plus the double integral on D2. Here, for example, in the picture, we see that this region of type 3 can be divided into type 1, because here we impose the limit here and the boundaries are only dependent on x, and here instead the region of type 2 has boundaries that are only dependent on y. In some situations, for example when we have a spherical symmetry, it is useful to change Cartesian coordinates to polar coordinates. We have that if the function is continuous on a polar rectangle given by having the radius in between two positive constants a and b, and the angle being in between alpha and beta, where the difference between beta and alpha is in between 0 and 2 pi, then the double integral on the region rectangle R is equal to the integral from alpha to beta and then from a to b of the function evaluated at here x and here y, that become r cosine theta and r sine theta, and then instead of dx dy we have r dr d theta. This formula can be generalized to the case where alpha and beta are functions of theta. But to see an image of this, the infinitesimal polar rectangle that we see here can be thought as an ordinary rectangle with dimensions r d theta and dr, and therefore has area dA as r dr d theta. We can see r here, r d theta, and the area is the green one that we see. So in the case we have a parametric surface, so a surface that can be expressed in 3D, having a vector equation r in uv that has a component x dependent on u of v in the I cap direction, plus y always evaluated in uv j cap plus z in uv k cap. Double integral results in the double integral in the region D. So the region D is the domain of R, in a way, of the function evaluated at the parametric equation R times the cross product between the component in U of R and the component in V of R. We can see here the function r taking every point on the domain of D into some point in the surface S. As a special case of this, we have that if F is a continuous vector field defined on an oriented surface S with unit normal vector n, which means that the surface has a orientation, Then the surface integral of f over s is given by this formula. So this is a surface integral that is equal to the function f dot product with the normal. This is referred as the flux of f across the surface S. We see now an application of double integrals. To find the moment of inertia of a particle of mass m, we usually use the formula mr², where r is the distance from the particle to the axis. We can extend this concept to a lamina that has the density function rho, that is dependent on x and y, and that occupies a region D. The result is that we have this formula, so the moment of inertia is equal to the double integral of y² that multiplies the function rho, and you integrate on a area D. As an example, now we find the moment of inertia of a homogeneous disk D with density rho, and the center, the origin, and radius a. The boundary of D is the circle x² plus y² is equal to a², but in polar coordinates it is described by theta being bounded by 0 and 2 pi, and r being bounded by 0 and a. Then, using the formula we saw, the moment of inertia is given by this integral, that in this case, since rho is just a constant, is rho that multiplies the integral from 0 to 2 pi, and then the integral from 0 of a of r sine theta squared r dr d theta. In this case, this was y, and rho has been taken out. This is dA. So this then becomes rho that multiplies the integral from 0 to 2 pi, and then here we take the things that depend on theta, so sine squared theta d theta. Now we have the other integral from 0 to a, and here we have things that depend on r, so we have r cubed dr. Then we simplify sine squared into a half 1 minus cosine 2 theta, so that it's easier to integrate this part, as we get theta minus a half sine of 2 theta, and the bounds are 0 and 2 pi. Of course, we took the half outside, and for the other integral it is easy. R cubed becomes r to the power of 4 divided by 4 from 0 to a. The result of this, in evaluating at the bounds that we have, is pi rho a square a to the power of 4 divided by 4. This was the end of the second video about surface integrals. See you on the next videos, where we will talk about volume integrals.